So this thing doesn't pick up super well. Limit of a function. We did limit last year. Remember doing that? Limit of a function. And of course, a function is a lot of fun. How fun is that? And watch how much fun this is. See? That's like more fun than you know what to do with. And we're done having fun. Okay. Remember this from last year? Remember the vocabulary? What's that called? Limit of the difference quotient. There you go. Limit of the difference quotient. And that's how we found the slope. That's how we found the derivative. You will see a number of variations on the theme of this equation. Make sure you can write that equation, blindfolded with one hand tied behind your back. Like I said, we'll see some variations on it. What will happen, and I've seen this question on the test, is they'll give you something that's kind of in that form, and you're supposed to go, oh, that's the limit of the difference quotient. All they're really asking me is, what's the derivative of the function? Even though it's in this form, and it kind of looks really complicated, and your brain starts to fry a little bit. Just the limit of the difference quotient is just the slope. We've dealt with limits a little bit. We're going to talk a little bit more about them. Next year in BC, that some people will take, not you, forgot for a second, the limit is much more a part of the course. We will just kind of go, oh, okay, with limits. The BC course delves into some of the subtle details of limit and puts a precise definition to it. We're not going to quite be so precise. First of all, we're going to talk about what's called a two-sided limit. When you see this symbol, limit as h approaches 0, that means I'm approaching 0 from either side of 0. I could be coming to 0 from the positive side. I could be coming to 0 from the negative side. Both sides. When you see that notation, limit as h approaches 0, or when it's anything approaches 0, it's a two-sided limit, both sides. You got to be approaching. So, two-sided limit. Get this on picture on your calculator and take a look at what it looks like. Go. Okay, so graph looks like this, right? Take a look at, something like that. Take a look at your table. Remember how to do that? Go second table and get near 4. Now, if yours is way up here in the boondocks, if you go to table set, second table set, you can change your starting value to whatever you're interested in seeing. Change that to 4. And now when you go to set table, it'll start you at 4. So now you can see. Now scroll back and forth a little bit near 4. So as I go second table, I can see, look at the values as what's happening. So when I'm at -1, I get 2, then I get -2, then -4, then -4 again, then -2, and okay, and 4 is 2, and then it goes 8, and so on, right? What a limit is about is what's happening near the point. The limit is about what's happening near 4. Now I'm gonna have you change it. Go back to table set and change the delta table to 0.05. Change the delta table to 0.05. So second, wrong button, second table set, and I'm going to still have my starting value at 4, but 0.05. So now when I go to table, I'm much closer in, right? So now look what happens as I look at either side of what's going on at 4. When I'm below 4, that's not going to let me write on this. It should. When I'm below 4, the value is 1.2. And then as I get a little closer, it's 1.5. A little closer, it's 1.7. And when I finally get to 4, it's 2. When I'm above 4, 4.15, it's 2.7. But as I get closer, as I move this way, it's getting closer and closer to 2. That's the whole premise of limit. What value are you approaching as x approaches, in this case, 4? As x approaches 4, my y values are approaching 2. 2 would be the limit. It's the value you're approaching. It's not necessarily what the value is at the point, it's the value you're approaching. As x gets closer and closer to 4, f of x gets closer to 2. Therefore, 2 is the limit. So if I wrote the expression, the limit as x approaches 4 of f of x, this f of x, the answer would be 2. Not because it equals 2, but because it's approaching 2. I don't care what's going on at the point. I care about what's happening near the point. That's what that notation is then. That's called a limit. The limit as x approaches a of f of x is equal to L. L is the limit, the value you approach. That's the way you read that. The limit of f of x as x approaches a is L. Don't write this down, but this is the key point. It's not about what happens at A, it's about what happens near A. I said it backwards from this. What is important is what happens near A, not what happens at A. Okay? Whatever the point A is. So if you glance at this equation, can you tell me what's going on with that? Do you remember? Say again? There's some discontinuity. Can you tell me what kind? Go ahead and graph this on your calculator. See what you get. And so look what we came up with. At least what I came up with. Did we come up with that? And so what's going on in 3? There's a hole. Now it doesn't show the hole, but up here at 3, there's a hole there. You just can't see it because it's infinitely small. 2.99999 is on the graph. 3.001 is on the graph. 3 is not. So there's a hole going on there at 3. So back to this question. What if then? So what happens at 3 is kind of key, but what happens near 3 is what the limit is about. At 3, this thing's got the hole, like you said. When there's a common factor, if I knew how to factor, I would let you know as well. When there's a common factor, you get a hole at that spot. And so there's a hole at 3. And then what you just get is the line x plus 2. Those guys go away. This function's undefined for 3. Now, the limit, though, even though the function's not defined at that point, the limit still exists. There's an answer. Because the limit doesn't care what's going on at 3. The limit is about what happens near 3. Go back to your table on the calculator and do a table set and do your starting value at 3. Leave those as 0.05. Wrong button. Wrong button again. What am I looking for? Table. There it is. So look at 3. You get an error at 3, right? But the limit is about the values that you're approaching. So I'm at 5.2, then to 5.15, 5.1, 5.05. And what value is it going towards? 1 to 5. What value is this guy going towards as I go the other way? As I come from 2.75 and work my way down, I'm getting bigger and bigger and bigger and bigger. Now I never get to 5. 5 is never on this graph. The limit is about what happens near the point. So the limit of this function is 5 as x approaches 3. Not about what happens at the point, it's about what happens near the point. The function's not even defined at 3, but I can still have a limit at 3. Graph this on your calculator. Take a look at what it looks like. Be in radian mode. So I'm graphing sine of x over x. Sine of x over x. clear sine of x divided by x, and I gotta make sure I'm in the right mode, and I'm gonna do a window. I'm gonna go -10 to 10 is okay, but only go to positive and -2 on the y scale. Now, why is it doing that? Keep in mind, we're dividing by x. Yeah. As x gets bigger and bigger and bigger, what's going to be happening? What's going to be happening as x gets bigger and bigger? The value of the fraction gets smaller and smaller. Sine of x simply goes back and forth between -1 and 1, right? But now I'm dividing by successively larger values of x. So when I take the sine of a million, I have no idea what the sine of a million is, but it's a number between 1 and -1, right? And then when I divide it by a million, I get a really, really small answer. But now here's the interesting thing. As x approaches 0, as this guy goes to 0, typically a fraction approaches what number? When the denominator of a fraction gets smaller and smaller and smaller, the fraction gets bigger and bigger and bigger. So you would think this thing should be going to infinity, right? But here's the kicker to this. What's the sine doing as x gets closer to 0? What's the sine of x? If I said what's the limit of as x approaches 0 of the sine of x? It's approaching 0. So the numerator is approaching 0, and the denominator is approaching 0. Well, but look at the picture. What's the fraction approaching? What look like? Thinking? 1. This is the value 1 up here, which I can't draw on this thing anymore. Used to be able to. It's 1. The answer to this problem is 1. Now, what's the function value at 0? Or we would say undefined. How come? Where'd it go? How come? We got an issue, right? The domain issue. The 0 in the denominator is not okay. So this graph actually, can't get it. This graph is one that crops up every once in a while. There will be some problems later on in this year that I will say, oh, you remember that day when I jumped up and down and waved my arms at you and said, remember this problem? And you're going to go, yeah. I did. Were you not? Did you not see me? I went. It's not a huge big deal by any means. There's like a couple of problems that come up this year where you're going to make something look like this, and you're just supposed to go, oh yeah, that's that problem. And I know the limit of that thing is 0. I'm sorry, 1, as I approach 0. The limit is 1 as I approach 0. I'm not sure I've ever seen it on the AP test, but you never know. Sometimes there are some things that are like kind of standouts. Oh yeah, that shows up all the time kind of thing, but not so much this one. But it'll crop up every once in a while. But the thing that's interesting about it, you would think there'd be like a vertical asymptote. Normally, if I had an equation 2x over x minus 5, at 5, I'd have a vertical asymptote. And this thing would go to, it would like go to infinity. Whoops, sorry. It would go to infinity as I got closer to 5. This one doesn't go to infinity because the numerator is going to 0 kind of at the same rate that x is going to 0. And actually, later on, what we're going to show this year is that the sine of x is pretty much, as long as you're near 0, the sine of x and x are pretty much almost the exact same answer. So the sine of 0.0001 and x equals 0.001 Well, the sine of 0.001 is going to be really close to 0.001. But we don't need that now. Different problem now, right? It's not the sine of x over x, it's the sine of pi over x. So what's going to happen as x approaches infinity? Let's kind of think this through and see if we can figure out what this looks like before we graph it. What's going to happen as x approaches infinity? What's going to happen to pi over x? It's going to get smaller. And so as pi over x gets smaller, that means the sine of that thing approaches what number? 0. But what happens as x gets smaller? You going to live? That would be great. So what's going to happen here that's interesting, we'll stop for a second. So what happens here is as x gets smaller and smaller and smaller, pi over x goes to infinity. Well, if this is going to infinity in here, think about what sine looks like as sine gets bigger and bigger and bigger. Sine looks like this, right? It goes on, 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 on. Stick that in your calculator and take a look at it. Let's see what the picture looks like. What's it doing in there? How many times do you think it does that in there?
I don't know.
Because as x goes to 0, that means, so the point I'm plotting is really close to 0. But as x goes closer and closer to 0, whoops, this guy's going towards infinity. How many bumps are there as you go to infinity? Lots. Maybe an infinite number of them. And so what you get is, with this picture, we can zoom in a little bit. You remember how I showed you how to zoom just in the x direction and not the y direction? So I'm going to go to, if I go to zoom and over to memory, we can set the factors, number 4. And so I'm going to let the x factor, I want the x factor to change, but I want the y vector to stay the same. I think that'll do it. So now when I go to zoom in, I should just change my x values. Yep, y values didn't change. Ooh, we got a bunch of bumps there. Let's do it again. Do it again. And no matter how many times you do this, zooming in, you will never get a clean picture, because between these 2 points, and I'm going to cheat them so I can draw on the thing. Ha! Showed you who's boss. Between here and here, there's an infinite number of bumps. Between these 2 x values, there's an infinite number in there. As you get closer and closer to 0, you get more and more and more rotations. Can't ever get in there. Now, back to this question. What's the limit as x approaches 0? What value is it getting closer and closer to? And the answer is the limit does not exist. Mean Girls. I've actually looked at that equation. She's right, the limit doesn't exist.
Was the girl said -1?
Is what?
One of the other girls said -1.
Yeah. I can't remember what it was. It was something, though. It was a fairly complicated one. Sometimes limits don't exist. If you don't approach the same value from both sides, then the limit doesn't exist. This function's undefined at 0, but that's not the problem. The problem is that this thing oscillates faster and faster and faster and more and more and more. So it's not getting closer and closer to 0 or getting closer and closer to 1 or getting closer. It keeps going back and forth and back and forth. It never gets closer and closer and closer. Some functions, their limit doesn't exist. Now you could pick any other point in the real number system. If I change this 0 to anything but 0, the limit exists because there's an actual point it's getting closer to. This one at 0, it doesn't exist. And so you can just say D N E does not exist. That would be a lovely answer. Everything we just talked about was what we called at the beginning a two-sided limit, where we come at this thing from both sides. You have to be approaching, when I did that graph and I would look at what x was 4, I approached 4 from above 4, I approached 4 from below 4. Kind of like what you guys did in the homework last night, right? You found the slope on the left, you found the slope on the right. One-sided limit. Let's look at what's going on this thing. First of all, see if you can figure out how this graphs. You remember how to do it piecewise, even without the calculator? You should be able to graph that kind of in a couple of seconds and get a picture of that. And if you think you have it, don't look yet. But if you think you have it, oh, you need the equation set. Cheater. All right. So it looks like that. It says if I'm greater than or equal to 0, the equation was 1. If I'm less than 0, then the equation was 0. So I get this. Look at the question now of limit. Does the limit exist? If I come to 0 from both sides, am I approaching the same value? No. The two-sided limit doesn't exist in this case. Look at how I've written this, though. And the subtle difference is this little guy right there. And this little guy right there. This is read, you read that as the limit as t approaches 0 from the right. Because of the little plus sign, because of that little plus sign right there, it's as t approaches 0 from the right. So as t approaches 0 from the right, I'm coming in this way. What value are you approaching as you approach 0 from the right? 1. Yeah. Now, as it turns out, you're already at 1, but just because you're already there doesn't mean you're not there. That's the limit. I don't know what that means. Now this guy says right there, because of the little negative sign, you read this as the limit as t approaches 0 from the left. And again, it's the negative sign that's the key thing. Don't read it as negative or positive, and the interpretation is just from the direction in this case. So from the right, from the left. And of course the limit in this case, even though the function doesn't exist at that point, all right, well, at this point down here it doesn't exist. It does exist up here, but it doesn't exist down there. But the limit from the left is still 0. I'm getting closer and closer and closer to 0, even though I'm already on 0. So the two-sided limit can exist. Now later on, we're going to talk about continuity. Continuity is whether something is continuous, whether it's one solid line. This is not continuous. And one of the reasons that it fails the continuity test is that the limit doesn't exist. The two-sided limit has to exist. You have to be approaching the same point everywhere on the graph. So if I'm not approaching the same point, the limit or it can't be continuous. Notice what this says now. This was h of t. I defined this function as h of t. And look at what this is saying about h of t now. What's the difference? Why am I suddenly saying it doesn't exist, even though back here I said, well, it equals 1, it equals 0. There's no plus or minus right here. And so this is a two-sided limit. Since the two-sided limit, since the limit from the left and the limit from the right don't equal each other, that means the two-sided limit doesn't exist. So look what this is saying. This is kind of a formal way of writing what I just said. Up here I'm saying, notice that there's no plus sign, right? It's just I'm approaching A. So this is a two-sided limit up at the top here. The two-sided limit exists if and only if. Now, if and only if is a very technical math phrase. That means it works both ways. That you could turn this thing around and it would be true. For example, Pythagorean theorem. A triangle is a right triangle if and only if a squared plus b squared equals c squared. And if I turn that around, a squared plus b squared equals c squared is true if and only if it's a right triangle. So it goes both ways. So here, now, this guy is saying the limit from the left. This guy's saying the limit from the right. And so if the limit from the left is equal to some number L, and the limit from the right is equal to some number L, then the two-sided limit is going to be equal to L. Just like we saw when we did the graph with approaching 4. It was approaching the number 2 from the left. It was approaching the number 2 from the right. The two-sided limit was 2. New title, infinite limits. That might tell you something about what's going on here. What's the value of the function at 0? What's this equal to at 0? Not the limit, just the function. 5. Yeah. Looks like that. Because it's x squared, they're going up on both sides. The x squared makes it positive on both sides. You don't have anything down below. 1 over x, if you remember, looks like this. 1 up and 1 down. But 1 over x squared, both of them are on the upper side. So what's the limit as x approaches 0? Remember, it doesn't matter what's going on at 0. Even though this thing's undefined, that's okay. But what value am I getting closer and closer to as I approach 0 from the right or approach 0 from the left? Is it getting, what number is it getting closer to? It's going to infinity. Is infinity a number? Sort of, no. Does this limit exist? No. Because it's not approaching a number. 10. If it was getting closer to 10, I could say 10. Infinity is not a number you can get closer to. It's always infinitely far away from you. It's not something you can get closer to. No matter how many steps forward that you take, it gets farther away. Since the values of x do not approach a number as x approaches 0, the limit does not exist. It's got to approach a number, and it's not. It's getting bigger and 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 bigger. Have I made my point? Bigger. So if it doesn't approach a value, the limit doesn't exist. But having said that, this particular non-existing limit non-exists in a particular way. And so we indicate that it doesn't exist by writing that the limit is infinity. That's a way of saying it doesn't exist. And it's describing how it doesn't exist. Remember the one that we had that did this? It came in this way. That limit doesn't exist. And there's no special way of saying how it doesn't exist. We just say it doesn't exist. This one, because it approaches positive infinity on both sides, this is a two-sided limit, right? There's no plus or minus right there. plus or minus there. It's a two-sided limit. So because I'm approaching infinity on both sides, I say the limit doesn't exist, and the way that I show that it doesn't exist is by putting infinity. It approaches infinity. Now look at the change. If I did this, the limit of 1 over x squared as x approaches infinity, that limit exists. As I go to infinity on this thing, I'm getting closer and closer and closer to 0. That limit exists. And if I put this little negative sign back up in here that I took out a second ago, and make it negative infinity, that also exists. As I go to negative infinity, I'm going to 0 also. So we sometimes talk, now, going to infinity is by definition a one-sided limit. There is no other side to infinity. Maybe Buzz Lightyear can get there, but we can't. So just a quick example. Back from last year, we should recognize that this is a limit at 3. There's going to be an asymptote, and it looked in something like this. And so a one-sided limit here is I approach from the right. Well, as I approach from 3 from the right, I'm going to positive infinity. As I approach 3 from the left, I'm going to negative infinity. Those limits don't exist. Existing has to be a number. That is not a number, pi, or what is that? Infinity, right? So it's simply a way of indicating how it doesn't exist. Not all of them exist in that same way. The important thing of limit is not what's going on at the point, it's what's going on near the point. The end. And that's the way it is. Here, you can sign your names on the end. So that forever people will know you. This is my big class this year. You can only do it one at a time. Oh, now she's gonna...
Oh no! Think it'll change the green?
Yes. She picked it up. All right. Wow! Now you're going to have to go watch this all the way through and get to your names at the end. Say goodbye.
Bye.
Say goodbye.